In this video, we are going to continue our derivation of the radiation that's produced by an oscillating electric dipole. So if you remember from the previous video, that what we have is some dipole with a positive charge and a negative charge that's now separated by some distance d. And what we're doing is measuring at some point in space the electric potential, V, okay, and there's all the parameters to it. So we're measuring the electric potential, and what we're doing is we're oscillating the positive charge and the negative charge back and forth along this dipole. So what we ended up with was the equation for the electric potential in terms of the dipole moment right here, as well as the driving frequency, which moves a charge back and forth along the dipole. Okay, so in order to get the electric field, then we are going to need to take the gradient of V, but we're also need to find the potential A. Okay, and just a reminder, we made three approximations. They were that the distance, the gap between the charges is much, much less than the distance to where we're measuring. The gap is much, much smaller than the actual wavelength of the radiation, and that our distance is much, much greater than the wavelength of the radiation. Okay, so now what we'll do is we will solve for A. So to get A, we'd have to know what the current is, and the current, as a function of time, is going to be the change in the charge with respect to time. In this case, the charge is oscillating up and down in the z direction. So that would be taking this derivative right here. So we get the constant charge Q0 times minus omega sine omega t, and that is in the z direction. Okay, so now we can apply that to get our potential, our vector potential A, as a function of position and time. And that equation is mu 0 over 4 pi, the integral, basically integrating over that distance that the current is traveling. And that's the current minus Q0 omega sine omega t minus r over c, so it's this retarded time, divided by the distance, and then all of that is in the z direction, and then we integrate over the path, dz. Okay, so we're going to integrate over essentially this path length here, dz, and we're measuring at a distance r and a distance script r from the actual amount of current, the current in dz. Okay, so we should probably write these in terms of r's and z's. So I can write script r from the law of cosines, r squared plus z squared minus 2rz cosine theta. And now if we apply that first approximation, where d is much, much less than r, or in this case, really r is much, much bigger than z. So if that is the case, then what we get is this term drops out, this term drops out, and r is essentially just the distance from the origin to the point in which we're measuring our potential. Okay, so that cleans things up a lot. We can now write the vector potential as mu 0 over 4 pi minus q naught omega sine omega times t minus r over c divided by r. And then the only thing that's left is the integral of dz from minus d over 2 to d over 2. Okay, so that's a pretty simple integral to solve. And so what you get is minus mu 0 q 0 omega d from the integral over 4 pi r times the sine omega t minus r over c. All of that is in the z direction. Now, since the dipole moment, P0, is just the charge times the distance, we can now write this with the dipole moment in mind. And what we have is minus mu 0 omega P0 over 4 pi r times the sine, all of that in the z direction. So that right there is now our solution to the vector potential A. Okay, so now to get the electric field, we've got to take some derivatives. And so first we'll start with the gradient of V, which is R dependent and theta dependent. So it's got those two pieces. So if you look back, you can see what the form of it is. And so what we get is, putting this all together, minus P0 omega over 4 pi epsilon naught times the speed of light times the cosine of, cosine theta times minus sine omega times t minus r over c, all of that over r squared, minus omega over rc cosine close that parentheses. Okay, and that's all in the r direction. So basically, taking the derivative of v with respect to r is just taking the derivative of that cosine function with respect to time. And then the theta part, we now have to basically take the derivative of cosine theta. So that gives us minus sine of theta over r squared times the sine omega t minus rc. And that is now the theta, that's the component in the theta direction. Okay. So if we now consider the approximation that r is much, much bigger than the wavelength, then that gets rid of some of this stuff. Basically gets rid of the sine right here in that theta part. And what we're left with is the gradient of V is all of these constants, c squared times, times cosine theta over r, cosine omega times the time part, and all of that is in the r direction. So r hat, they're crammed in on the end of the line. Okay, so now let's take the time derivative of a. And that's going to give us minus mu 0 p0 omega squared over 4 pi r times the cosine of omega t minus r over c in the z direction. So we have an electric field which has basically a radial component and a z component. Now, if you think about it, I can now write that z component in terms of r and theta. So if you look in the back cover of Griffith's textbook, you can see that the z unit vector is cosine r minus sine theta hat. So we could put that into the equation for the electric field. Okay, and now what we get is something, well, let's just write out all the components first. Minus P0 omega squared over 4 pi epsilon naught c squared times the cosine of theta over r times the cosine of omega times the time. That's in the r direction, plus mu 0 p0 omega squared over 4 pi cosine theta over r cosine the time part of the equation. So that's in the radial direction, minus mu 0 p0 omega squared over 4 pi sine theta over r cosine omega times the time in the theta direction. Okay. So now the interesting thing is that if you remember that the speed of light squared is 1 over mu 0 epsilon naught, or essentially epsilon naught c squared is equal to 1 over mu 0. So when I do that, I notice that I get this term here, the first term, is exactly the same as the second term, because I've got this epsilon naught c squared turning into 1 over mu naught. So now the radial components of the equation cancel each other out. And what I'm left with is just the theta dependence. So I get E is equal to minus mu 0 p0 omega squared over 4 pi sine theta over r times the cosine of omega t minus r over c, all of that in the theta direction. And that is my solution for the electric field that you would get from an oscillating dipole. So it's kind of interesting. So before we move on to the magnetic field, just want to take 1 minute just to kind of discuss this. And so what you see is that our electric field now is entirely in the theta direction. That, you know, our if you remember what our dipole looked like, we had this positive and negative charge. There was this wire that connected them. I oriented it such that this is the z direction here, and I'm measuring out here in some point in space at some distance r, and this is theta. And so our electric field now is entirely in the theta direction. So there's no r hat component to the vector. Okay, so in the next video what we'll do is we'll now work on the magnetic field, and then we'll pull it all together to come up with a solution for the radiation of a dipole.